tomorrow, November 11th, 2025, a date amateur astronomers have been waiting for. After 3 long weeks hidden behind the Sun, the interstellar object known as Three-Eye Atlas will finally return to view. For the first time since it entered our solar system, you won't need the Hubble Space Telescope or a professional observatory to see it. Just a backyard telescope, a dark sky, and a little patience. Right now, Atlas shines at magnitude 11 to 12, the brightest interstellar visitor ever observed at this stage. By comparison, Oumuamua, discovered in 2017, was a faint magnitude 20, invisible to amateur observers. Borisov, the comet spotted in 2019, only reached magnitude 15 at its peak, barely within reach of large telescopes. But Atlas is different. It's brighter, closer, and perfectly positioned. For the next 6 weeks, before it fades forever into the cold darkness between the stars, this will be your one true chance to witness an object from another world with your own eyes. The amateur astronomy community has been preparing for this moment since early October, when Atlas slipped behind the Sun on October 21st, 12 days before its closest approach. All ground-based observations stopped. Professional instruments could still track it through solar satellites, capturing its October 29th perihelion and a few mysterious post-pass anomalies. But for everyone else, the sky went silent. Now, that silence ends. November 11th marks Atlas's return, and from observatories to suburban rooftops, across 6 continents, thousands of stargazers are ready. For weeks now, the astronomy community has been preparing for this moment. Observation guides have circulated online, detailed sky charts tracing Atlas's slow journey night by night as it drifts through the constellations Virgo and Leo. Enthusiasts have shared equipment tips for every kind of setup, from compact backyard telescopes to advanced astrophotography rigs. Across continents, coordination networks have formed, ensuring that as Earth turns, Atlas will be tracked continuously from one observer to the next. But this isn't just about seeing it. Though glimpsing an interstellar object with your own eyes is an experience few will ever forget, the real purpose runs deeper. Citizen science. Every image, every light measurement gathered by amateur astronomers helps fill the gaps that even the world's largest observatories can't cover. Together they build a more complete picture of this visitor from the stars. In the pre-dawn hours, Atlas will rise quietly above the eastern horizon, glowing faintly a few hours before sunrise. The exact timing depends on where you are, but for most observers in the northern hemisphere, the best view begins around 4 a.m., looking east-southeast. At first, it will sit low in Virgo, then gradually drift into Leo as the weeks pass. Through the eyepiece, it won't dazzle, just a soft, fuzzy speck barely distinguishable from the background stars. But that speck has travelled for light years across the void. It was born around another sun shaped by another world's gravity, and now, for a fleeting moment, it passes through ours, the first and only time in human history. Atlas's predicted brightness, between magnitude 11 and 12, places it right on the edge of what most amateur telescopes can detect. Under truly dark skies, an 8-inch scope should be enough to spot a magnitude 11 object. At magnitude 12, you'll need something a bit larger, 10 to 12 inches of aperture ideally. Bigger instruments help, but they're not essential. What matters most is the quality of the sky and the steadiness of the air. The real challenge isn't finding it, it's recognizing it. Stars appear as sharp points of light. Comets, even faint ones, always look a little different. A soft, diffused glow instead of a pinpoint. If the air is still and your telescope's optics are well aligned, Atlas should reveal a subtle coma, a delicate haze surrounding its core, the faint signature of an active interstellar visitor. For many observers, photography will make the task far easier. A camera mounted on a telescope can capture long exposure images, revealing objects far too dim for the naked eye. Amateur astronomers often use DSLRs or dedicated astro cameras, shooting exposures from 30 seconds to several minutes. By stacking those frames, combining them digitally to reduce noise, they can reveal details invisible in a single shot. With careful stacking, even magnitude 13 or 14 targets emerge from the darkness. That means Atlas, at magnitude 11 or 12, should be well within reach of modest setups. But astrophotography isn't just about seeing, it's about recording. Every image taken of Atlas becomes part of the scientific record. Large observatories can't watch the sky every night. Their schedules are full and weather often gets in the way. Amateur astronomers fill that gap. If Atlas suddenly brightens, they'll see it first. If its coma develops new jets or asymmetries, they'll capture the change. And if its path begins to drift from prediction, their precise measurements will refine its trajectory through our solar system. Each photograph, each frame, is a small contribution to understanding a traveller from another star. We've seen this story before. In the 1990s, when Comet Hale-Bopp blazed across the sky, amateur astronomers around the world tracked it night after night. Their images and measurements revealed sudden outbursts, subtle variations, and evolving structures that even the largest observatories missed. When the data were compiled, the amateur record turned out to be more extensive, more continuous, and, in many ways, more valuable than anything produced by professional facilities. With Atlas, the potential is just as remarkable. Over the next 6 weeks, thousands of telescopes across the globe will be trained on a single distant point of light. Together, they'll generate millions of observations, brightness readings, positional data, even spectroscopic measurements from skilled amateurs equipped with small spectrographs. Combined, this will form a massive living data set, one that could equal or even surpass the professional record. At the heart of this effort is the Amateur Asteroid and Comet Observer Network, a loosely organised but globally connected group of enthusiasts who share their findings online. For Atlas, they've launched a coordinated monitoring campaign, inviting participants to observe the comet whenever weather allows and upload their results to a central open-access database. That database is updated in real time, allowing anyone, scientist or stargazer, to watch Atlas evolve night by night, and by tomorrow evening, it will begin to fill with the first post-perihelion data, the first ground-based observations of 3i Atlas since it disappeared behind the Sun in late October. Each new data point marks not just another number, but another connection, a moment when humanity scattered across the planet looks up together toward the same visitor from the stars. For those without telescopes, there's still a way to be part of the story. Across the world, live streams from amateur observatories will broadcast Atlas's return in real time, a collective window into an interstellar traveller's path. Online communities will share their best images, frame by frame, as the comet moves against the stars. Social media will light up with updates, discussions, and awe. You don't need expensive equipment to join in, only curiosity and a sense of wonder for what's out there. But if you do own a telescope, or know someone who does, tomorrow night is your moment. Find a dark sky, far from city lights. Set up your scope. Aim it toward the coordinates listed in the observation guides. Atlas's position will shift slightly each night as it glides through the constellations, so rely on updated ephemeris data or real-time astronomy apps to track it. Then search for that faint fuzzy dot. Take an image, compare it to a star chart, and when you confirm that what you're seeing is indeed 3i Atlas, take a moment to realise you're looking at something that shouldn't be here, an object that has travelled across the galaxy, now passing just 1.8 astronomical units from Earth. For scientists, this reemergence is a critical window. For the past 3 weeks, Atlas has been invisible to ground-based instruments, hidden behind the Sun. Solar monitoring satellites followed it through perihelion, recording its position and brightness, but they lack the tools for deeper study. Now, ground-based telescopes will fill that gap. Starting tomorrow, spectroscopists will analyse the composition of its coma, searching for signs of change since October. Imagers will capture the delicate structure of its tail and any new jets or asymmetries that have appeared. Photometrists will measure its light curve with precision, watching for fluctuations that might reveal rotation, outgassing, or internal activity. Every telescope pointed skyward, every image, every data point, adds a new piece to the puzzle. Together, they'll help us understand not just what Atlas is, but where it came from, and perhaps what stories it carries from beyond our Sun. The first week of observations, November 11th through November 18th, establishes the baseline. What is Atlas's brightness compared to predictions? Is it brighter, indicating increased activity, or dimmer, indicating it's fading as expected? What does the spectrum show? Are the molecules detected in August and September still present, or have they changed? Does the coma show structure, or is it diffuse and featureless? The answers to these questions will shape expectations for the December 19th close approach. If Atlas appears normal during the first week, matching models for a natural comet at this distance from the Sun, the December observations become tests of the natural hypothesis. Maybe the perihelion anomalies were transient, artifacts of peak heating that won't repeat. If Atlas appears anomalous, brightness higher than predicted or spectrum showing unexpected features, the December observations become confirmation. The anomalies aren't isolated, they're persistent. And persistence is harder to explain naturally than one-time events. Amateur observers won't resolve the question of whether Atlas is natural or artificial. Their data isn't precise enough for that. But they'll contribute context. Professional telescopes observe for hours per night at most. Amateurs observe whenever clear skies allow, providing continuity. If Atlas undergoes a sudden brightness change, an outburst or dimming, amateurs are more likely to catch it happening. If the object's motion deviates from predictions, amateurs provide additional position measurements that improve orbit determination. The combination of professional precision and amateur coverage produces a data set richer than either could achieve alone. There's also something deeply personal about this moment. When Oumuamua swept through the solar system in 2017, almost no one saw it. It was discovered too late, already past its closest approach, dimming and racing away before telescopes could track it. Borisov, 2 years later, was brighter, but still beyond the reach of most amateur eyes. For most people, these interstellar visitors were just stories, distant headlines, images captured by professionals. But Atlas is different. For the first time, an object from another star system has come close enough, bright enough and steady enough for ordinary people to see it. If you have a simple 8-inch telescope, a clear sky, and a little patience, you can witness it yourself. You can photograph it. You can look into the eyepiece and know that the faint fuzzy glow you see is not from this solar system. It was born around another sun, and now, by chance, it passes before your eyes. This opportunity will not come again soon. Interstellar objects are rare, a few discoveries a year, most already fading when we find them. The odds of another one appearing this close, this bright, within a single human lifetime are slim. Atlas may be the only interstellar visitor you'll ever see with your own eyes, and tomorrow that chance begins. So how do you actually observe it? Where do you point your telescope tomorrow night? And what does it take to see an object that's travelled light years, just to pass quietly through our solar system? The mechanics are simpler than you might think, but the preparation matters. Atlas isn't a brilliant comet with a sweeping tail cutting across the night sky. It's subtle, a faint hazy speck that rewards patience, precision, and a truly dark sky. Around the world, amateur astronomers are readying their telescopes for tomorrow's reemergence, planning every detail. Location comes first. Atlas will appear in the predawn hours, between midnight and sunrise, the deep silent window when the eastern horizon darkens and the comet climbs above the thick layers of atmosphere. For most observers across North America, the best viewing time falls between 4 and 6 a.m. local time, depending on latitude. Those farther east will see it rise earlier, those to the west a little later. But by 6 a.m. the first glow of dawn will begin to wash over the stars, stealing away the contrast that faint objects need. The 2 hours before sunrise are the sweet spot, your best chance to catch Atlas before daylight wins the sky. its celestial path is shifting night by night. On November 11th, Atlas will lie within the constellation Virgo, near its border with Leo. Virgo is easy to find. Look for its brightest star, Spica, a striking blue-white beacon shining at magnitude 1.0, dominating the southeastern sky in mid-November. Atlas will sit roughly 15 to 20 degrees from Spica, inching northward each night. By late November, it will cross into Leo, gliding past a nebula, the bright star marking Leo's tail. By mid-December, it will rest near the centre of the constellation, higher above the horizon, lingering longer before dawn, offering one last window for those who wish to see it before it fades forever. Pinpointing Atlas in the night sky isn't guesswork. It requires precision. The comet's position shifts slightly each night, so astronomers rely on what's known as ephemeris data, updated coordinates that track its motion across the heavens. Several online tools make this simple. NASA's Horizon system lets you enter your exact location and generate a custom chart of right ascension and declination, hour by hour. The free program Stellarium includes Atlas in its database, projecting its path across a realistic sky map. And mobile apps like Sky Safari or Starwalk do the same in real time, guiding your telescope with augmented sky overlays as you hold your phone to the stars. For November 11th, 2025, around 5 a.m. Eastern Standard Time, Atlas will sit near right ascension 13 hours 45 minutes, declination -8 degrees, a quiet patch of sky in Virgo, about halfway between Spica and the golden star Zavijava in the constellation's northwest corner. The object drifts roughly half a degree per day, about the width of the full moon, so last night's coordinates won't help you tomorrow. To stay on target, update your ephemeris each night or use an app that refreshes automatically. As for equipment, what you'll need depends on your goal. For visual observation, aperture is everything. Under dark skies, an 8-inch Schmidt-Cassegrain or Dobsonian telescope should reveal Atlas as a faint, misty patch of light around magnitude 11. A 10 or 12-inch scope will make detection easier, showing a more defined coma and allowing observation even in less than perfect conditions. Smaller instruments, 4 to 6 inches, might catch a glimpse under exceptional clarity, but it will be difficult, and binoculars, no matter how powerful, simply won't do. The comet is too faint, too small, and too far away. Photography, fortunately, is more forgiving than the human eye. A simple DSLR camera mounted to an 8-inch telescope can capture Atlas with exposures as short as 30 seconds at ISO 1600 or 3200. Take 10 or 20 frames, then stack them using programs like Deep Sky Stacker or PixInsight, and the faint blur of light begins to take shape, emerging from the noise as a clear, defined presence. Even when a single image shows only a hint, the combined result reveals the interstellar traveller in stunning detail. For those using dedicated astronomy cameras, called CCD or CMOS sensors built for long exposures, the results are even more impressive. These instruments routinely capture magnitude 13 or 14 objects with ease, pulling faint light from the edge of visibility. Many amateurs use the same cameras for photometry, measuring brightness precisely by comparing Atlas's glow to nearby reference stars in the same frame. In doing so, they transform their backyard setups into genuine scientific instruments. But there's one essential element every astrophotographer knows: tracking. As Atlas drifts slowly across the background stars, the telescope must follow perfectly to keep the comet centered. Most modern mounts do this automatically, using motorized tracking systems that match the sky's rotation. The gold standard for imaging is the German equatorial mount, which aligns with Earth's axis and uses a single motor for smooth, precise motion. Alt-azimuth mounts, common on Schmidt-Cassegrain telescopes, use dual motors but require field rotation corrections during longer exposures. For Atlas, the good news is that speed isn't an issue. Its apparent motion is slow, only a few arcseconds per minute, so small tracking errors won't spoil your shot. With steady alignment and patient exposure, the comet will hold its place in your frame, a faint reminder of how far it has travelled to appear there at all. Finding Atlas in your telescope's field of view will likely be the most challenging step of all. Even with precise coordinates, centering a faint magnitude 11 object requires patience and practice. The process astronomers use is called star hopping. It begins with a bright, easily recognizable star, one you can see with the naked eye, and then moves step by step toward the target, using progressively dimmer stars as guideposts. For Atlas on November 11th, that journey starts with Spica, the brilliant blue-white star anchoring the constellation Virgo. Begin by centering Spica in a low-power eyepiece to give yourself a wide view of the sky. Then, with the help of a star chart or digital sky map, slowly guide your telescope northward toward the coordinates where Atlas should appear. As you move, pause to identify the intermediate stars that match your chart, subtle confirmations that you are on the right path through the darkness. When you reach the predicted location, switch to a higher power eyepiece or activate your imaging camera. Study the field carefully. Stars will appear as sharp, pin-like points, clean and defined. Comets, even faint ones, will look different. Soft, diffuse, with a gentle haze surrounding a slightly brighter core. If you spot a fuzzy patch where a star should be, you've likely found Atlas, a speck of dust and ice from another sun, glowing faintly in your view. If you don't see it right away, don't give up. Ephemeris predictions carry small uncertainties, often a few arc-minutes, meaning the object may sit just outside the expected position. Widen your search, scan slowly, and trust your technique. When that faint glow finally appears, you'll know you're looking at something older than our solar system itself. Once you think you've found Atlas, the next step is verification. The sky is full of faint, fuzzy shapes, and not all of them are comets. To confirm your sighting, compare what you see against star charts. Take a photograph of the field and load it into software like Astrometrica or nova.astrometry.net. These tools automatically identify background stars and overlay catalogue coordinates, revealing exactly where your telescope was pointed. If the unknown patch aligns with Atlas's predicted position, you've found it. If not, you might be looking at a galaxy or a nebula. Both can appear comet-like through a small telescope. The key difference is motion. Atlas moves. Capture the same field again the next night. If the object has shifted by about the width of a full moon, it's not a galaxy. It's our interstellar visitor, quietly gliding across the backdrop of the stars. Once confirmed, it's time to document your observation. Record the date, time, location and details of your telescope setup, aperture, focal length and camera settings if you took images. Add visual notes. Was the coma round or elongated? Did you notice a brighter centre or the trace of a tail? Each detail, however small, helps refine the world's collective understanding of Atlas's behaviour. Upload your images to the Amateur Asteroid and Comet Observer Network, or share them through communities like Cloudy Nights or the British Astronomical Association's Comets section. Every contribution counts, and if you don't have your own telescope, there's still a way to see it. Many local astronomy clubs and amateur observatories host public viewing sessions for events like this. Around November 11th, check for gatherings in your area. These sessions often feature large telescopes, guided explanations, and the excitement of shared discovery. You'll stand beneath the same sky, among others who have come to witness something extraordinary, a visitor from another star system, seen together for one fleeting moment in time. For those who can't step outside beneath a clear sky, live streams offer a window to the same experience. Across the globe, amateur astronomers are preparing to broadcast their observations of Atlas in real time. Beginning November 11th, channels on YouTube and Twitch will share live telescope feeds, often accompanied by commentary explaining what viewers are seeing as it happens. Among them, the Virtual Telescope project, led by Italian astronomer Gianluca Massi, has announced multiple streaming sessions throughout November and December, allowing anyone, anywhere, to witness this interstellar visitor without the need for equipment, or even good weather. The observation window lasts until December 21st, about 6 weeks of visibility. During that time, Atlas will fade steadily as it travels farther from both the Sun and the Earth. By late November, its brightness will slip to magnitude 12 or 13, visible only in larger amateur instruments. By mid-December, it will reach magnitude 14, barely detectable even through advanced imaging, and by late December, magnitude 15 or fainter, it will be gone to all but the most powerful telescopes. The earlier you look, the easier it will be to see. Tomorrow, November 11th, is the moment of opportunity, but even the best equipment is nothing without the right sky. Light pollution is the greatest enemy of faint object astronomy. In cities where streetlights and buildings cast their glow into the heavens, a magnitude 11 object simply vanishes into the haze. From a dark rural site, far from artificial light, the same object appears easily, a soft, steady glow against the black. If you live under bright skies, make the journey, drive to darkness, find a remote field, a stretch of desert, a quiet patch of farmland, anywhere you can see the Milky Way with your naked eyes. That level of darkness is the difference between an empty sky and a once-in-a-lifetime encounter with a visitor from beyond our sun. Another factor that shapes every observation is the moon. A bright moon washes out the sky just like city lights, drowning faint objects in its glare. Fortunately, on November 11th, the moon is a waxing crescent, setting before midnight and leaving the predawn hours in deep darkness. Perfect conditions for spotting Atlas. But this won't last. By late November, the moon waxes toward full brightness, and by early December, it begins rising in the early morning hours, flooding the sky and interfering with comet observations. The solution is simple. Plan around the moon. Choose nights when it sets before midnight, or rises only after your viewing window ends. Then there's weather, the unpredictable wildcard of astronomy. Clear skies are essential, and November across much of North America can be uncertain. Clouds are merciless. Even a thin veil of cirrus is enough to scatter starlight, reduce contrast, and erase faint targets from view. Always check forecasts and satellite imagery before heading out. If clouds spoil your session tomorrow, don't be discouraged. Atlas will remain visible for weeks. One missed night means nothing. In skywatching, persistence always pays off. The more often you look, the greater your chance of catching those rare moments of perfect seeing, when the air is calm, the stars are steady, and your telescope reveals the sky in stunning clarity. For some observers, this is more than a single night's effort. It's a campaign. Across continents, dedicated amateurs are planning nightly observations to monitor Atlas continuously. Each night brings a new data point. Small brightness variations that reveal outbursts or fading trends, tiny positional shifts that refine the comet's orbit, delicate spectral changes that trace its evolving chemistry. These campaigns are global collaborations, with observers in different time zones passing the baton from one to the next. As dawn ends observation in North America, Europe takes over. When Europe finishes, Asia begins. Together they form a planet-wide relay, ensuring that, for 6 remarkable weeks, humanity keeps a near-continuous watch on a traveller from beyond our sun. For most observers, just 1 or 2 clear nights will be enough. The moment you find Atlas, faint, distant and real, is unforgettable. Seeing an interstellar object with your own eyes changes something inside you. The universe stops feeling abstract. It becomes immediate, alive, personal. You're no longer reading about it in an article or watching someone else's footage. You're capturing it yourself. Photons that left another star system, now landing on your retina, your camera sensor, your world. That connection, fragile though it may be, is one of the rarest experiences an astronomer can have. So tomorrow night, when you turn your telescope toward Virgo, searching for that faint fuzzy point of light, remember what you're truly looking at. You're seeing something older than the sun, forged in a place we can only imagine. A fragment of another world, cast adrift by gravity we'll never witness, travelling for millions of years through the cold between the stars now gliding silently through our sky. This is not just a comet. It is a messenger from another system crossing paths with ours for a brief and fleeting moment. A meeting that happens once in a civilization's lifetime. When you find it, make it count. Here's what makes Atlas different from every other interstellar visitor we've ever found. You might actually see it. Not just a data point on a screen, not just a faint line in a survey image, but a real, visible object through your own telescope. When Oumuamua was discovered in 2017, it was a ghost, a magnitude 20 speck, invisible to anything but the largest professional instruments. It was seen only as a streak of pixels, already fading, already leaving. Borisov in 2019 was brighter but still a magnitude 15 object, requiring massive amateur telescopes and long exposures just to glimpse a smudge of light. Atlas is different. At magnitude 11 to 12, it's bright enough that observers using 10 or 12-inch telescopes can actually see structure, not just a point of light, but a faint tangible form. Cameras will reveal even more, subtle textures in the coma, shifting patterns as sunlight interacts with ice and dust. And with 6 full weeks of visibility, there's time to watch it change, to see an interstellar traveller evolve before your eyes. So, what might you actually see when you look through the eyepiece tomorrow night? The first thing is the coma, the soft, hazy envelope of gas and dust surrounding the comet's nucleus. As sunlight warms its surface, frozen gases sublimate, carrying dust outward into a diffuse glowing sphere. The coma shines brightest at the centre, fading slowly into the blackness beyond. For Atlas, the coma's true size spans hundreds of thousands of kilometres, yet from 267 million kilometres away, it appears tiny, only a few arcseconds across. Still, in a 10-inch telescope at 100x magnification, that difference is just enough. The coma won't look like a star. It will appear soft, extended, alive, a delicate smudge of motionless light that connects your small patch of sky to the deep, endless space between the stars. The central condensation, that faint brightness at the very heart of the coma, is the key feature to watch. Every natural comet shows some degree of it, a subtle peak of light where the nucleus and the densest gases reside. Its intensity reveals much about a comet's activity level. Highly active comets, small but energetic, display strong central condensation, a bright core enveloped by a wide, diffuse halo of dust and gas. Weaker comets, less active or fading, show a softer profile, their light spread more evenly across the coma. For Atlas, this has been changing. Observations in July and August showed moderate condensation, a steady, modest activity level. Then, in September, around the time of the so-called green glow event, observers noted a rise in brightness near the core, a sign that Atlas was waking up. Now, 12 days after perihelion, the question remains, is that activity still building, or beginning to fade? What astronomers see in the next few nights will tell them. Detecting a tail is less certain, but not impossible. Tails form when solar wind and radiation pressure sweep gas and dust away from the coma, drawing them into delicate streams that always point away from the sun. At 1.8 astronomical units, where Atlas now travels, those forces are strong enough to sculpt a tail, but faintly. To the eye, it may remain invisible. Through long exposure imaging, however, photographers might capture a whisper of it. A slight extension on the anti-solar side of the comet, a pale arc revealing how sunlight shapes matter drifting through interstellar space. The length, the angle, the brightness gradient, each offers a clue about the forces at work and how much material Atlas is shedding as it glides through the inner solar system. Colour is another detail worth watching. To the human eye, most faint celestial objects look colourless. That's because our retina's cone cells, responsible for colour perception, need far more light than these distant objects can provide. Below magnitude 10, nearly everything appears in shades of grey, no matter its true colour. But cameras tell a different story. With colour-capable sensors or short exposures through colour filters, They can reveal hues hidden from human sight, the secret colours of a comet. For Atlas, those colours have already shifted over time. During the September 7th green glow event, spectroscopy and imaging showed the coma shining vividly in green wavelengths around 500 nanometers. Later, during perihelion on October 29th, new observations revealed a blue emission, centered near 450 nanometers, shorter wavelengths, higher energy. Tomorrow's data will tell whether Atlas still glows with these spectral colours, or whether it's faded back to the more typical reddish hue seen in ordinary comets. That reddish tone is the cosmic baseline. Most comets wear a subtle coat of organic molecules that absorb blue light and reflect red, giving them warm shades of amber, copper and brown when seen in visible light. If Atlas photographs red, it's behaving as expected, reflecting sunlight off dusty organic material. But if it shines green or blue, something different is happening. Green emission comes from molecules like diatomic carbon and cyanogen, excited by ultraviolet sunlight, gases glowing as they release absorbed energy. Blue emission, especially when stronger than predicted, hints at thermal processes or even fluorescence from exotic molecules, reacting to solar radiation in ways rarely seen before. If those colours persist tomorrow, they won't just make Atlas beautiful, they'll make it mysterious. Evidence that what we're seeing is more than just reflected sunlight. It's an active conversation between a traveller from another world and the light of our own star. Spectroscopy, the art of decoding light, is a rare but powerful tool in the hands of amateur astronomers. Only a few dozen enthusiasts around the world have the equipment to do it, but for those who do, the rewards can be extraordinary. A spectrograph attaches to a telescope much like a camera, but instead of capturing an image, it splits the light from a celestial object into its component wavelengths. A prism or diffraction grating spreads that light across a detector, creating a spectrum, a barcode of the universe, showing bright emission lines and dark absorption bands that reveal what the object is made of. Professional spectroscopy of Atlas has already identified several familiar molecules: carbon dioxide, water, carbon monoxide, diatomic carbon, and cyanogen, each detected at different stages of its journey. Amateur instruments, though less sensitive, are still capable of detecting the strongest features, especially the green emission near 500 nanometers if it remains active. If you manage to capture a spectrum tomorrow night, and it shows unexpected emission lines, wavelengths that don't correspond to any known cometary molecules, that's something extraordinary. Upload it immediately to the online analysis forums where professional spectroscopists can review your data. Even modest amateur spectrographs can detect major anomalies if they're strong enough. If Atlas is emitting light from metallic vapours, industrial compounds, or high-temperature plasmas, they will reveal themselves as distinct lines at very specific wavelengths. Sodium at 589 nanometers, nickel near 350 to 360, iron around 370 to 430. Detecting such metallic lines would be unprecedented, a hint that Atlas might not be entirely natural, that somewhere in its distant history it may have carried more than ice and dust across the stars. Beyond any single telescope or photograph, the true strength of this campaign lies in the collective data, the thousands of independent observations gathered by amateur astronomers around the world. Alone, one observation can be uncertain. A small increase in brightness might be a measurement error. A faint streak resembling a tail might be camera noise or optical artifacts. But when dozens of observers, scattered across continents, record the same change independently, the evidence becomes undeniable. That's the power of statistics in the sky. One observer may glimpse a possibility. 50 turn that possibility into a discovery. This approach has a long and proud tradition in astronomy. When comet Shoemaker-Levy 9 collided with Jupiter in 1994, thousands of amateurs across the globe documented the event. Their data revealed details of impact timing, fireball brightness, and atmospheric ripples that professional telescopes, limited in number and location, could not fully capture. In 2007, when When Comet Holmes suddenly brightened 1,000,000-fold in a matter of hours, it was amateur astronomers who provided continuous monitoring, minute by minute, creating a timeline of the outburst that remains unmatched. Now, with Atlas, the same collective power is at work again. Over 6 weeks of observation, hundreds of telescopes will sweep the same patch of sky, night after night. Together, they'll produce a dataset richer than any single observatory could achieve, a mosaic of global collaboration. From mountaintops and city rooftops, deserts and backyards, the world will watch as one, building, night by night, the most complete portrait ever assembled of an interstellar visitor passing briefly through our solar system. Timing is everything. Professional observatories, with tight schedules and limited access, might capture Atlas only once a week, single snapshots separated by days. But amateur astronomers are out every night, sometimes multiple times in a single evening, building a continuous record of change measured in hours. That constant vigilance gives them an advantage. If Atlas experiences a sudden brightness outburst, a surge of activity in its coma, it will be the amateurs who see it first. If that outburst lasts only a few hours before fading, they might be the only ones to record it at all. This has happened before. Several comets in the past decade revealed brief flares of light, visible only in amateur data, missed entirely by professional telescopes simply because they weren't looking at the right moment. For Atlas, such short-lived events could be diagnostic, a clue to its true nature. Natural comets brighten over hours or days as sunlight reaches hidden pockets of ice, releasing vapor and dust in bursts of activity. But if Atlas were to flash or flare for minutes or even seconds, that would defy natural explanation. Ice doesn't sublimate and stop that quickly, but engines can. Short, sharp spikes in brightness, captured in amateur light curves, plots showing magnitude over time, could signal something far more complex than geology. A brief pulse of energy, a controlled maneuver, a system releasing heat, gas, or radiation in sudden bursts. If such patterns appear in the data, they would point to a profound possibility that Atlas is not behaving like a comet at all. Another quantity that can be measured is motion, the silent drift of Atlas across the stars. Each night its position changes ever so slightly as it traces its path through the solar system. Amateur astronomers equipped with astrometry software can measure this motion with remarkable precision, pinpointing the comet's right ascension and declination to within a few arcseconds. Over weeks, these measurements refine its orbital path, sharpening predictions of where it will be next. But there's more at stake than simple tracking. When an object deviates from its predicted path, it reveals the presence of non-gravitational forces, subtle accelerations that gravity alone cannot explain. If Atlas is being pushed, slowed, or redirected by something other than the sun's pull, that deviation will show up in the data. At perihelion on October 29th, astronomers detected exactly that, a non-gravitational acceleration. Just 3 days later, on November the 1st, Atlas was already 5,000 kilometers ahead of where purely gravitational models said it should be. It's a small difference, less than 1/100th of a degree across the sky, but measurable. And if the acceleration continues, the shift will grow. By mid-November, it could reach 10,000 to 15,000 kilometers. By December, perhaps 50,000 or more. Amateur astrometry, collected night after night from around the world, can confirm this behavior independently, strengthening what professional observatories first detected. Every coordinate, every plotted point, adds to the emerging story. If Atlas is still accelerating, the numbers will tell us. The sky itself will tell us. If the shift stops, if Atlas's position once again matches what gravity predicts, that too is meaningful. It would suggest the acceleration was temporary, limited to the days around perihelion, when the comet was closest to the sun. In that case, natural explanations fit. A burst of outgassing triggered by peak solar heat, briefly pushing the object off course before fading away. But if the shift continues, or worse, increases, then the story changes. As Atlas moves farther from the sun, its outgassing should decline, not intensify. Continued acceleration under those conditions would defy natural physics. It would suggest something else: propulsion. The visibility window from November 11th through December 21st gives us 6 weeks to find out. Professional observatories have scheduled precise observation slots: Hubble on December 15th and 16th, the James Webb Space Telescope on the 17th, and radio arrays from the 18th through the 20th. But between those dates lie long, quiet stretches where no professional eyes are watching. That's where amateurs come in, filling the gaps, providing continuous coverage night after night. If something happens on November 25th, a sudden brightness spike, a trajectory shift, professionals won't see it unless amateurs detect it first and raise the alarm. And that's why this campaign matters. Amateur observations aren't just for personal fulfillment, though the joy of seeing an interstellar visitor is reward enough. They are scientifically essential. Because what we're watching might be the most important astronomical discovery in human history, or it might be an ordinary comet behaving in ways we don't yet fully understand. The answer will come only from data. As much as we can gather in the short 6 weeks Atlas remains within reach. Every image, every brightness curve, every spectrum, every coordinate recorded by observers around the world brings us closer to the truth. So tomorrow night, when you aim your telescope toward Virgo and focus on that faint, delicate patch of light, remember, you're not just looking at a comet. You're participating in the most important observation campaign of the decade. Here's the reality that makes these 6 weeks irreplaceable. After December 21st, Thriss Atlas will fade beyond the reach of amateur telescopes, forever. By Christmas Day, it will dim to magnitude 13 or 14, visible only with professional-grade instruments and pristine skies. By New Year's 2026, it slips to magnitude 15, accessible only to research observatories with massive mirrors and perfect calibration. By February, it will be magnitude 17, detectable solely by Hubble and the world's largest ground-based telescopes, and by summer 2026, it will fade beyond magnitude 20, effectively gone, invisible even to our most advanced instruments. At that point, Atlas will be racing back into interstellar space at 40 kilometers per second, leaving our solar system behind forever. These 6 weeks, starting tomorrow, are the only time in human history that anyone will ever see this object through personal equipment. That finality gives every observation a new weight. You're not just looking at a comet, you're witnessing something that will never return, something no future generation will ever see again, a fragment of another world, crossing our skies for a fleeting moment before vanishing into the dark between stars. Oumuamua is gone, now 5.5 billion kilometers away, speeding outward into the void. Borisov is gone too, fainter still, lost to time and distance, and soon Atlas will join them. By this time next year it will lie beyond Neptune's orbit, invisible, unreachable, remembered only in the data gathered during these 6 precious weeks. That makes every clear night a gift. Every observation matters. If clouds cover the sky tomorrow, wait for the next opportunity. If November 11th is lost, try the 12th or the 13th. But don't wait too long. Each passing night, Atlas fades a little more, from magnitude 11 to 11.5 to 12 and beyond. The lesson is simple. Observe early, observe often. Catch Atlas while it's still bright, while the skies are clear, while it still belongs to us, before it drifts back into the deep silence from which it came. The December 19th close approach, just 39 days from now, marks the centerpiece of the entire observation campaign. That's when Through-Eye Atlas passes closest to Earth, when Hubble's resolution is at its sharpest, Webb's infrared sensitivity reaches its peak, and radio telescopes across the globe turn their antennas to listen with utmost precision. But those few days of professional observation don't tell the whole story. The weeks leading up to December 19th are just as important. That's when amateurs provide the context, the slow, continuous record of how Atlas behaves, how it brightens or fades, how its coma evolves night by night. Their data establishes the baseline behavior and flags anomalies that professionals can investigate in real time. Without that steady coverage, the great observatories of the world would be working blind, capturing isolated moments without knowing whether they represent the norm or a fleeting exception. Consider this scenario. It's December 5th, 2 weeks before the close approach. An amateur astronomer in Australia takes a photograph of Atlas and notices something unusual. It's suddenly brighter than expected, shining at magnitude 11 instead of 12.5. The image is posted online. Within hours, observers across the world confirm the brightening. Word spreads quickly through the scientific community. Professional astronomers, who hadn't scheduled observations for that night, mobilize. Telescopes are retasked. Within minutes, spectra and high-resolution images are being captured. The outburst is recorded in full detail, revealing its cause, perhaps a pocket of ice suddenly exposed by sunlight, or perhaps something else entirely. Without that amateur discovery, the event would have gone unnoticed, hidden between professional observation windows, its data lost forever. Instead, a single image shared online becomes the trigger for a global scientific response. That's the power of the collaboration, the bridge between backyard telescopes and space observatories, between curiosity and discovery. This isn't a hypothetical scenario, it's how astronomy truly works. Professional telescopes can't watch everything all the time. Their schedules are full, their targets planned weeks in advance, so they rely on a global community of amateurs, thousands of patient observers who scan the skies each night. Supernovae are often discovered first by amateurs, watching galaxies flare suddenly with light from a dying star. Variable stars are tracked for decades by dedicated volunteers, building continuous records no professional program could ever sustain. Asteroid occultations, those brief moments when an asteroid passes in front of a star, are captured by networks of amateurs across continents, their combined timing revealing the asteroid's shape and size. For Atlas, the same principle applies. Professionals may hold the world's most powerful instruments, but amateurs provide the eyes they lack, the unbroken coverage between scheduled observations. It's a partnership that keeps watch over the changing sky. Yet the 6-week window ahead carries more than scientific weight. It carries emotional meaning. We live in a time when most cosmic events reach us through screens, distant and abstract. We read about black holes merging, galaxies colliding, stars exploding, but we don't experience them directly. Atlas is different. For these few weeks, it's visible. You can see it yourself. You can photograph it. You can share it, showing friends, family, or students that faint, ghostly point of light from beyond our solar system. That tangibility is rare in modern astronomy, and it matters. Somewhere tomorrow night, a child will look through a telescope for the first time and see Atlas, a tiny fuzzy dot that isn't a star at all, but a traveller from another sun. They'll remember that moment for the rest of their lives. Years from now, they'll tell their children and grandchildren about it, how their parents, their teachers, or a local astronomy club helped them witness an interstellar visitor with their own eyes. For some, that memory will ignite a lifelong passion for the cosmos. For others, it will simply remain a quiet, beautiful reminder that the universe is not distant or unreachable, but alive and near, waiting patiently above us night after night. For adults, the experience carries a different kind of weight. We understand impermanence. We know that opportunities like this don't return. When Atlas fades in late December, it will be gone, and we may never see another interstellar object this bright, this close, this accessible again. Yes, the discovery rate is rising as new survey telescopes scan the heavens more deeply each year. More interstellar objects will be found, but most will be faint, discovered only after they have already passed, or positioned too low, too distant, or too dim for amateur eyes. Atlas is an accident of circumstance, a rare convergence of brightness, proximity, and timing. It's bright enough to see with modest telescopes, close enough to resolve faint structure, and visible long enough for the world's stargazers to watch it unfold under clear northern hemisphere predawn skies. The scientific legacy of these 6 weeks will stretch far beyond the winter nights that contain it. Millions of images, thousands of spectra, and countless brightness and position measurements will be analysed for years. Astronomers will compare Atlas to Oumuamua and Borisov, searching for patterns, shared traits that define how interstellar visitors behave when they cross our system. Models will evolve, theories will rise and fall, and debates will continue as scientists try to explain what we saw, or to admit that perhaps it cannot be explained naturally. And if the technological hypothesis, the idea that Atlas might not be entirely natural, begins to hold, if the data points to design rather than chance, then these 6 weeks will be remembered as more than an astronomical campaign. They will be remembered as humanity's first recorded encounter with technology from another world. But that answer, whatever it turns out to be, won't come from any single observation. It will emerge from the accumulation of data, the pattern that takes shape when hundreds of observers over 6 continuous weeks document 3 Atlas with patience and precision. Professional astronomers provide accuracy, high-resolution measurements, spectroscopy, and orbital modelling. But amateurs provide something just as valuable: coverage. Their nightly vigilance fills the gaps between scheduled sessions, building a dataset broad enough and deep enough to tell the true story. Together they form a partnership, one that may finally answer the question, what is 3i Atlas? The answer may not arrive quickly. Even after December 21st, when the comet fades from view, uncertainty will remain. The data might reveal behaviours that challenge natural explanations without offering definitive proof of anything artificial. And that's the reality of science. Sometimes clarity comes slowly. The debate could continue for years, with every interpretation grounded in one thing: the data gathered during these 6 precious weeks. And in that data, amateurs matter just as much as professionals. Every exposure, every brightness measurement, every coordinate logged into a spreadsheet contributes to the foundation of our understanding. That's why tomorrow matters. November 11th isn't just the day Atlas reemerges from behind the sun. It's the beginning of what may be the most important amateur observation campaign in the history of interstellar astronomy. What you see tomorrow night, what thousands of observers across the planet will capture in the weeks ahead, could reshape our understanding of the universe and our place within it. This isn't exaggeration. These are the stakes. An object from another star system is passing through ours, behaving in ways no one fully understands, and for 6 brief weeks, it's visible to anyone with a telescope and the determination to look up. If you're hearing this and you have the equipment, observe tomorrow night. If you don't, find someone who does. Astronomy clubs welcome visitors. Public observatories host viewing sessions. And for those under cloudy skies or in cities too bright for stars, live streams will open windows to the same event in real time. Don't let this opportunity slip away because you assume someone else will record it. Every observer counts. Every image matters. Every brightness or position measurement adds another point of truth to the growing picture of what 3i Atlas really is. And if you do observe, share what you see. Post your images on forums, upload your data to community databases, discuss your findings with others. The amateur astronomy community has always thrived on collaboration, and Atlas is uniting that community like few objects ever have. Observers in California will hand off to Europe, then to Asia, each watching as Earth turns beneath the stars. It's a global relay, a network of ordinary people bound together by a single, extraordinary object. 48 hours from now, Atlas will finally re-emerge from behind the sun. The glare will lift, and once again it will become visible to telescopes on Earth. And for the next 6 weeks, perhaps the most important 6 weeks in the history of amateur astronomy, the sky belongs to all of us, not just professionals, not just institutions with billion-dollar observatories, but everyone. Anyone with a telescope, a camera, or simply a clear sky has a chance to watch a visitor from another star system pass through our own. If you've stayed with this journey through the observation guides, the equipment checklists, and the meaning of these 6 irreplaceable weeks that might help answer humanity's oldest question, consider liking and subscribing for more explorations of the wonders we can still see with our own eyes. Share your thoughts in the comments. Will you be observing tomorrow night? What do you hope to see when you look toward the stars? Because now the countdown is over. Tomorrow, November 11th, Atlas returns to the sky. For 6 weeks, it's ours to observe. And after December 21st, it's gone, forever. The telescopes are ready. The coordinates are calculated, and in just 48 hours, thousands of observers around the world will aim their instruments toward Virgo, searching for that faint, fragile point of light. This is your chance. Don't miss it. Sweet dreams and clear skies.